Right, so great question. The first thing I'd like to think about with something like this is just drawing a diagram. So I'll do that now. All right, so great question. The first starting point I'd look for here is drawing a little diagram. So this represents our initial velocity with both components, but we can then separate this out into an initial velocity in terms of our I direction, an initial velocity in terms of our J direction. So in the I direction, it's going to be 30 because that's the hypotenuse of this triangle here. And then it will be cos of 36 degrees because we're looking at this side here, which is going to be the cosine ratio of this angle in here, 36. Similarly, for our J component, it's just going to be 30 sine 36 degrees. And so these are important to come back to later on when we're working through our vector calc. How I generally like to portray vectors is with column notation. If you prefer I's and J's, totally fine. I just like columns because it's a bit less to write out, and I think it makes more visual sense for me. So I'm just going to write the initial velocity instead of that as instead 30 cos 36 degrees, 30 sine 36 degrees as a column vector like that. Cool. So we know the initial speed of 30 meters per second. We know the angle of 36. We know we're using vector calculus here. And now we've got to figure out what we're doing with this 10-meter high wall. So we need to determine whether the ball will clear a 10-meter high vertical wall that is 70 meters horizontally away. And yeah, we're assuming a resistance gravity. Cool. So what we can add to our diagram now then is a wall over here. We can just say if it's there. And that wall is 70 meters from where we start. And because we want to figure out whether the ball will clear this wall, what we're trying to model now is the position of the ball. We need to figure out, is the position of the ball here when it goes past the wall? Is it here? Is it some other place? Essentially, we need to figure out, is the J component at 70 meters higher than 10? And so that's what we'll work backwards through now. So if we remember our vector calculus for projectile motion, what we can start with is r dot dot t. And what this represents is acceleration in terms of time. So r double dot is the same as our acceleration. And because acceleration, the only thing contributing to acceleration is gravity. And that's in the J component, the J direction. We can write our acceleration in terms of a vector as 0 for the I direction. And now this is up to you. You can do G. What I like to do at this stage is actually make a statement and say, let up and right be positive directions. So it's relative. You can make this G here, like that, if you're saying that downwards is positive. But if that was also the case, you'd have to adjust things like this initial velocity. That's now going in the negative direction relative to that. So I always like putting upwards as the positive direction, and all you have to account for there is making this negative G here. Cool. From there, we can now use our calculus to find what velocity would be. And this is r dot with respect to t. And keep in mind here, all of these equations for acceleration, velocity, position, you can remember, but they're not on the formula sheet. So I think it's good practice to be able to work backwards from acceleration, which is kind of your default, because it just has one component, and then be able to work that back to position. Okay, so when we go from acceleration to velocity, we are going to integrate. And what we'll get here is 0 is just going to integrate to 0. But importantly, we've got this plus c here, so I'm going to write that as plus c1. Negative g then is going to become it's going to become negative gt, because we're integrating with respect to t. And then it's also going to get a plus c2 there. So that's what we'll get on the next line. But the good thing about this step here is this is velocity, just here. And this here is our initial velocities. So we actually know what this equals, and we know what this equals at the initial point. So what we can do is we can work backwards and find these actual c values. So we're not left with just these unknown values heading into our position. Okay, so what we do next then is we can say that, all right, when time equals 0, because this is initially, 0 plus c1 equals 30 cos 36 degrees. Obviously this is just 0, so therefore c1 is just our initial I velocity. Cool. Similarly, negative gt plus c2 is 30 sine 36. But remembering here, we're looking at when t is 0, so this is actually then 0, and so it's the same result. So c2 is just, again, our initial velocity. You don't necessarily need to go through that process to figure that out, but I think, again, it's good practice. So then what we can say is that our velocity in terms of time as a vector is going to be 30 cos 36 degrees. And then our j component is going to be negative gt plus 30 so 36. Right. So carrying on now here, we need to find our position in order to be able to model the motion of the ball. And what that is just one more integration away from where we were. So we've got velocity. Now to find position, it's just r without a dot in terms of t. And again, we're integrating here, so I might just actually write it out properly this time. So this is the operation we're working. And so we've got to integrate each of these components separately. So what do they look like? There's actually no t component here. So this entire top part will just become everything times t. So I'll just write it like that. And in a second, we can actually evaluate 30 cos 36 if we need. Okay. And in this bottom part, we've got kind of two components. So the first bit, also there's going to be a plus c here. And I'm going to say plus c3 to not confuse it with these plus c's. Okay, and then on the bottom part, we've got negative g t, then we've got to add 1 to the power, so t squared, got to divide by the power over 2. And then similarly, we've got 30t sine 36 degrees plus c4. And that's what we've got there. Then the question is, well, how do we resolve these c values? And what we can do there is we know that this initial point here, we can say that's the origin. And by that, we can say that at time 0, the position of the particle is 0, 0. from this, we can use the same theory we used up here to equate each of our I and j components to get a value for c. And here, we can look ahead and just see that if this is 0, if this is 0, and if this is 0, each of the c values are going to have to equal 0. And so what we can just do there is, well, therefore, the position with respect to time has to equal just 30t cos 36 degrees and negative gt squared over 2 plus 30t sine 36. And that's then our model, our model for motion ball. Okay, the second part of this problem then, if you like, involves figuring out, will this ball clear a 10-meter wall when it's 70 meters away? And so I think something that we want to try and figure out here, first of all, is at what time will the ball be at this 70-meter mark? We don't know quite yet where it is, like it might be here, it might be here, it might be here. But we want to figure out, okay, how long does it take to travel there? And then once we know the time, we can try and substitute that back into our second part, our j component, and figure out what the height is. And so what I'm going to do here is we know that the position at a certain time, sorry, we'll use so the position at some time that we're trying to figure out is 70 meters. We also know that our position equation is 30t cos 36. So that has to equal 70. To make it easier on ourselves, we want to actually evaluate what this 30 cos 36 equals. So if I do that in my calculator, we can find that that's then 24.27 roughly. T equals 70, and now this is just a simple equation. T is 70 divided by this 24.27, which is about 2.88. 2.88 seconds. And once we know that, we can then substitute back into this I component. So we'll look at R dot in terms of I at 2.88 seconds. And again, that's roughly, like with your calculator. You don't want to round this off and then just type in the rounded number. You want to try and keep it as specific as possible. So you use like the previous answer and you click like the answer button rather than typing it in. Just to make sure you get that decimal right, particularly if it's a question where it's like saying, look, to 2 decimal places or something like that, or even an exact value. You want to make sure that you're getting that precise thing, but I don't think that says, yeah, it doesn't. Okay, so we're subbing in 2.88, and again, that's just going to be, oh, sorry, not into our component, to our j component. This is our I component. Okay, so that's looking at this second one now, and so we can just go, okay, well that's, and I'm going to simplify this out. So we can assume that g is 9.8. So I'm just going to write that as 9.8 divided by 2 is 4.9. So 4.9 times 2.88 squared. Then we've got plus 30 times 2.88 sine 36 degrees. And so from here, it's just calculator work again. So if I put that in my calculator, I would get 10.18 meters. And then so if we look back at the question, it was asking, determine whether the ball will clear a 10-meter high vertical wall at 70 meters horizontally away. Okay, so maybe that's 5 marks. The 6th mark might then be, therefore, the ball will clear the 10-meter vertical or some kind of word response to that effect. Okay, so what we went through here is it's a vector calculus problem with applications to projectile motion. We worked backwards from acceleration to find a position function here, and that found the model. We also created a diagram just to make it a bit easier for ourselves, evaluated the initial velocity in both the I and j component, and then we applied that to solve for our c values. So then we just had a full equation here that we could work with. We then used our known horizontal displacement to find a value for t, sub that into our j component for position to find where that ball would be at that time and at that horizontal position, which was slightly above 10. So the ball would clear the vertical wall. Cool. Hope that helps. Thanks.